Hello students, good evening all. So welcome to our session. So today in today's session we are going to start our next chapter, that is indefinite integrals. So basically it is a part of our integrals. So in this entire topic of integrals we have started with our indefinite integrals, and the next topic that we are going to cover is definite integrals. Right, so this is our first session on this particular chapter of indefinite integrals. So basically in this indefinite integrals, so there will be few properties which we will be seeing, and actually we can use the same methods of integration which we have used in our indefinite. Then what will be a difference and what will be the thing we can see the differentiating between the definite integrals as well as our indefinite integrals. So before getting into the part of it, so let's quickly have a overview of our today's session of definite integrals. So we are going to start with the brief introduction. So like what is this definite integrals and all, and which inclusive of the definition. So in the introduction part we are actually inclusive the definition of what is this definite integrals, as well as how we are going to represent that of a definite integrals. So that will be coming under in our introduction as well as the definition of our definite integrals. Right, so typically here we will be seeing like how we actually write it in a different way, like how we actually represent here our definite integrals. When coming to our indefinite, like you obviously see the difference directly, because if we represent the thing, then it will be easy for us to differentiate. And coming to the most important part of our session will be the properties. So when it coming to the definite integrals, mostly the most important things are nothing but the properties, because by using the properties of integrals itself, we can solve lots of questions which are related to our definite integrals. So we'll be focusing a bit in our properties of integrals, and corresponding to the each of the property, we are going to solve questions related to that, so that we'll be it will be handy for you guys to do and apply these properties of integrals, because in a question there won't be any mentioning of this particular property we have to use. So it had to be our thing, like which property we have to use, when it has to be applicable. So that will be coming through by practice alone. So that's why we are going to focus a bit on our properties of integrals. So when we are dealing with each of the property, and corresponding to that, we'll be solving the questions related to the each of the properties of integrals. So in and overall, so in our today's session, we are just having a quick introduction to our definite integrals and what's the representation of it. And then we are jumping into the properties of integrals, which is our most important concept here, right? So let's start with the introduction part as well as the definition, we can say. So let f of x be a continuous function which is defined on an interval. Right, so basically how we actually write our integral. So what is our representation of any integral? It can be a definite or indefinite. So this will be the symbol, and if we are having any function, so that will be written it like this. Right, so once we differentiate this function, what will be the result? In our result also we will be having some function in terms of the variable x or not. Right, so let that be f of x. And along with that, we have seen in our indefinite integrals, to our result after integrating it, there will be a constant added. So if I am having a function f of x, and if I want to integrate that, the result will be something like this. Capital F of x, that means a function in terms of x plus some constant c. Right. So when it comes to, this is in our general indefinite expression. So when it comes to the definite, so how will we do that? So here we will be taking this function f of x. So that is given to be a continuous function which is in the interval, which is defined in the interval of a comma b closed. So in this interval, the function f of x is continuous. Right. That means we will be taking these two limits. So a and b, we can say they will be a critical points here. We can say them as limits, right, for the function f of x. Right, so these two limits will be coming here, and then our function f of x is alone, we are saying it is continuous only in this particular closed interval, that is a comma b. So in another interval we don't know because it doesn't mention here. So according to the given information, we will be following in this way, that our given function f of x is continuous in this closed interval a comma b. Then our limits will be a and b because our function is varying from a and b, which is a continuous function here. So we'll add up the limits to our integrals and we'll be representing like this, which means for this indefinite integral, we are going to add our limits. So this is a and b. So this is how we'll be adding our limits. So once we add our limits to the integral, so it's obvious that they'll be continuing after the integration also. Yes or no? So then what it will become? So they'll be turning out to be, so integration of our f of x dx from the limits a to b. So they'll be written, so capital X. So for this x also they'll be, for this function also we'll be having the intervals from a to b. So how we actually write these intervals? So these will be written as our capital F of, so we'll be substituting the upper limit here, that is f of b, and minus the function which way substitute the lower limit. So this will be our definite thing, right? So this is called our definite integral of the function f of x within the given limits, given interval limits a and b. So once they have mentioned the interval, we can directly take them as our limits and we can write our definite integral of the given function f of x. Right. So the interval a comma b here is nothing but called to be the range of the integration, because that is the only values we'll be having. So that interval here which is given, that limits, so that is called to be the range of integration. Right. So here for every definite integral, we'll be having a unique solution, right? Because the limits are given. And if there is one more condition, we can find the c also, and then we'll be having a definite solution here, right? So in and overall, if we compare, whenever we are having a limits, that will become our definite integral, and the representation of the definite integral you can see here, right? So you already know if a function is given, how to integrate that, because that and all we have learned in our indefinite, right? So we already aware of how to do this integration part. So now we are just improvising it by adding the limits for that function, and when we add the limits, it will be turning out to be f of x, some limits a to b. So this actually means, this actually meant to be this expression. That means by substituting the upper limit in the function minus substituting the lower limit in the function. So this will be the expansion or the representation of that. Right. So this is all about our typical introduction or definition and the representation of our definite integrals. So here I am not going to discuss how to integrate the function and all, because we have already discussed the methods of integration. We have already seen the standard integrals of differentiation, basic properties, everything we have covered. Right. So here how can we even do it by applying that? So that we will be seeing here. So as we have seen what is actually the definition of our definite integrals. So let's get into it and solve a quick question here. So here comes the first question, guys. Can you guys solve it and let me know what's the answer for this? Because the thing here is you have to integrate it and then substitute the limits. Right. So that's the basic difference. And you know how to integrate any given function. So quickly, can you do it? So here we are having a function that is integration to secant square x. So we can separate here actually because we are having plus. So I am going to separate it. So here limits are from 0 to pi by 4. So I can separate 2 secant x, secant square x as one function plus. So the limit will be added to each of the functions. So x cube dx. Here also the limit will be same, 0 to pi by 4 plus, and the next function is 2. So integration of 2 dx, and the limits are same here, 0 to pi by 4. So instead of taking the direct function here, I have splitted it so that our integration actually makes a bit easier. So now you can integrate it and let me know what's the answer, guys. So if you are having any questions how to do it and all, you can let me know. I'll just help you with that. But in this, you should be aware of only two basic formulas. What will be our integration of secant square x and what will be the integration of x power n. So these are the only things we should be aware of. Integration of secant square x and integration of x power n. So if we guys are aware of these two basic formulas which we have seen, then it's easy to get the answer for this particular question here. So let me know if anyone of you finished solving this question. Okay, Siddharth has already given the answer. Okay, fine. So let's wait for a few more answers. So once we're done with the integration, the next step will be the substitution of our limits. So here, this is our first function where 2 is constant. So we can pull out 2. And what will be our integration of secant square x? That will be tan x. So it will be tan x. And after integration, we will be writing the limits here. 0 to pi by 4. Okay, even Syam has given the answer. Okay, fine. So those who are having any doubts, you can look at here. I'm just simplifying it. So, and then what about the integration of x power 3? That will be x power 4 divided by 4. And here it will be 0 to pi by 4. And then here again 2 is constant. If there is nothing, we will be having x here. That is from limit 0 to pi by 4. So now our thing is we have to substitute here. So that will be 2 tan pi by 4 minus 2 tan 0. Right? And then here, so in place of x, we have to substitute. So this will become pi power 4. So divided by 4 power 4 into 4. Right. Minus, even if we substitute 0, that will be 0. So no need of it. And then 2 into pi by 4 here. And then minus 0 anyways, that will become 0. So now here we are having 2. So let me write it here. So what is the value of tan pi by 4? That is our tan. 45, it will be 1. So it will become 2 here. And 0, the other part. So 2 plus. So pi by 4 divided by what is the value here? So 4 power 4 into 4. The value will be around 1024. And then we are remaining with 2 pi by 4. So 2 will get cancelled here and we'll be remaining with pi by 2. Right. So this will be our direct answer here. Right. So for definite integrals, as they have mentioned the limits here, so we won't be having any constant. So directly the answer will be integration from 0 to pi by 4. So this will be equal to 2 plus pi by 4 by 1024 plus pi by 2. So this will be our answer. Right. So the only thing we should be aware of here is how to substitute these limits, because the integration part and all you are already aware of it because you are doing entire thing from the chapter of indefinite integrals. So there is nothing new in that. So the only thing we are learning new here is to the substitution of this limits and then simplifying it further. Right. So I hope you guys got this point. So let's just have one more question on this and then we'll just move into our properties of integrals. So here comes the next question. So quickly guys, it's a very easy question. So here instead of the finding the integral value, you have to find the constant k value here, because the integral value has already given here, which is equal to 0. But the procedure will be the same thing, how we'll be finding the integral. Okay, most of you got it. Siddharth, Shyam, Lakshmi and all. Okay. So let's just do this, guys. So here also in this function, you can split the function and then you can integrate it and you can equate to our integral value which is given, so that we can easily find the constant value k here. So let's guys, so what is the given integral here? So let's just write down here. So from the limit 0 to 1, the function is 3x square. So we can split it again, 3x square dx 1, and then plus integration of 2x, the limits will be 0 to 1, and then integration of k, so here it will be dx, k dx, and the limits are 0 to 1, and this entire integration value is given to be 0 here. Okay, two of you has given the answer, Siddharth and Shivaranjani. Okay, so what about others? So let's just wait for two more answers and then we can move ahead. Quickly guys, if any of you solved apart from these two, you can just ping me. And if anyone has any questions, any doubts also, you can let me know. So here what will be the integration of this particular integral? So it will be 3x cubed by 3. So limit 0 to 1. So we can directly eliminate this. And then plus 2x square by 2, limit 0 to 1. So this will also be eliminated. And here k, so it will be kx 0 to 1. This will be equal to 0. Okay, Shyam is also given. So our function here will be x cube plus x square plus kx from the limit 0 to 1, which is equal to 0. So if we substitute 1, this will become 1 plus 1 plus k. And if we substitute 0, so this will be 0 plus 0 and 0. So this entire thing will be equal to 0, which is given in the question. So now if we simplify it, we will be having, so 1 plus 1, 2. So 2 plus k will be equal to 0. From here, the value of k is nothing but directly equal to minus 2. Right. So this is the way how we will be simplifying it. So then I think there is nothing new of doing this integral here. So the only thing is substitution of the given limits here. So that's the only new thing we are doing here. Right, so this is the quick basic introduction and how to do this basic integrals of substituting the limits and all. So now let's get into the most important concept, that is our properties of integrals. So the first property here is integration of f of x dx from the limits a to b. So that will be equal to integration of f of t dt, integration of f of u dt. That means here whatever the variable can be. So here in this property, they are saying that whatever the variable can be. It can be a x, it can be a t, it can be a u. So we can actually do that. So here we can say our x is nothing but a simple dummy variable. It can be replaced by any other. So it's in some questions it depends, because here in place of x we have simply written t. In place of t we have simply written u. That means x equal to u, t equal to c, that we can see. But in case if our function x, function t equal to some function in terms of x, then there will be changing of the limits. So this point you have to keep in mind. So here directly there is no change here. So in place of x variable we are writing some other variable. So it's the same thing. But if our t is again some function in terms of x, then again our limits will be varying. So that we'll be seeing and learning in further sessions. But here the only thing is there is nothing new. We are just using a variable. So here you can see 0 to pi by 2. We can write it as sin x dx, sin t dt, sin u du. Anything can be written here. So there is the thing here. It's only a variable. Right. So coming to our next property here. So if once we are having a integral of any function within the limits a to b. So here I am having the integral of function f of x from the intervals within the intervals a to b. So this can be written in another way, that is I can change my limits. So instead of if my limits are a b closed, then in general what I will be writing, so a to b. So if in case I want to write it to be b to a, which means I am actually changing the direction. So I am actually changing the limits here. Then a minus will be added here. Right. So integration of a function f of x dx from the limits a to b can be written in another way by simply changing the limits. That is nothing but minus of integration of the function f of x dx from the limits b to a. So here the point, the catch, you have got it right. So the thing is we are just changing the the limits, right? So that is nothing but our interchange of the limits. So when we interchange the limits, so there will be a sign change here, right? So when we interchange the limits of the given function, we have to note the thing that the sign will be changing here, right? So moving on to the next. So here comes the next property. So here if you observe, we are having a integral, that is integration of function f of x dx within the limits a and b. Because c is lying in between my limits a and b. So here c is my value which is lying in between my two limits a and b. So here I can even split my function within these intervals, and I can rewrite my integral, that is integration of a to b f of x dx can be written as a to c. So integration of function f of x dx within the limits a to c, and then adding that to my function of f of x within the limits c to b. Right. So I have taken the value c within b and c. So I will be taking a to c one interval and then c to b one interval, and then I add it. That will be directly equal to my integral from a to b. So this is one more property which we can see here for our integrals, right? So in general, this property is used when the integrand has two or more rules in the integration interval. So if we are having two or more rules which we have to follow, then we will be applying this particular rule of our property 3. So in general, I can say when we have a modulus, right? Because if the interval has given, modulus actually depends upon the value, it will be changing, yes or no? So we can actually split the function based upon this interval in general where we are having a modulus function. So we will be doing examples of it, so no need to worry. So you can see here only we have taken one c value. Like that, you can take some number of c values in between the a and b intervals, the a and b limits, and you can split the integral in this way. That is, if my integral is from the limits a to b, so integration of function f of x dx from limit a to b, so this can be written as integration of a to c1 and then c1 to c2, c2 to c3 until whatever number of values I have taken in between my two limits of a and b. So this is my third property of the integrals here, right? So before getting into the next property, let's solve a question here. So as I mentioned, this splitting property which we have seen right now, that is our third property, is mostly applicable when we are having a modulus function. Because for a modulus function, it is obvious that it will be varying. Because if we substitute one value, the expression inside the modulus gives negative. For some values, the expression inside the modulus gives positive. right? But whatever the inside expression give positive or negative, the modulus give out to be the result to be a positive, right? So that's why we'll be using this property splitting method, and then we'll be writing the function whether it's positive or negative inside expression, and accordingly we'll be solving the integral here. So here you can see this question. Can you guys give it a try for a second? Can you guys look at the question, and can you guys give a try for at least 1 or 2 minutes, and then we can have a discussion. If anyone could able to solve it, you can please let me know. So how can you split this function f of x here? Like what can be the limit value you can pick up in between the limits 0 to 2? So here what are our limits value? 0 and 2. So what will be the value which we can pick in between so that it will be splitting our function, modulus function? Just think a bit. So most of our modulus questions will be solved in this. Is it buffering? I don't think so. If anyone face the same problem, you can just let me know so that I'll just check it once again. So by looking at the function, by looking at the modulus function here, what can be the limits here? What can be the split value which we can take? So here the function is obviously 1 minus x, which means the cut will be x only in between 0 and 2. So here I am having my modulus function 1 minus x. Right, what will be the inside expression if my x value is lying in between 0 less than equal to x less than equal to 1? So if it's in between 0 and 1, will it be a positive or negative? So 1 minus 0 and all, it will be, so it will be directly taken to be 1 minus x. Whereas if I am having from 1 to 2, then it will be the value, if it is greater than 1, 1 minus greater 1 value will be obviously a negative value, which means here I will be getting a negative, which means minus of 1 minus x, which can be written as x minus 1. That means the splitting point, the breaking point for this function here is nothing but 1. Right. So from 0 to 1, you can see that the function, the modulus function will be equal to 1 minus x, whereas from the limits 1 to 2, it will be turning out to be x minus 1. So now how can I split and write my given function? So this can be written as integration from limit 0 to 1. The function will be 1 minus x dx. And from the limit 1 to 2, it will be x minus 1 dx. So once we could able to crack this and we could able to write in this way, and the next steps are very easy because we know how to do this integration and find the answer here. Right, okay, Siddharth has already given the answer. Is it 2? Okay, you have given 2. So let's see what about others. If anyone has got the same answer, please let me know. So let's just integrate it, guys. So here, okay. So this will be x minus x square by 2, and the limits are 0 to 1. And for the second, this will be x square by 2 minus x, and the limits are 1 to 2. Right, so we cannot combine this function and write it because the limits are different here. So let's substitute 1. So 1 minus 1 by 2. And 0 if we substitute also, it will be 0 also. So no need to do that. And for here, if we substitute 2, it will be 4 by 2 minus 2. Right. Minus, if we substitute 1, that will be 1 by 2 minus 1. So now I will be having 1 minus 1 by 2 plus, so this will be 2 minus 2, 0, minus 1 by 2 and then plus 1. Right, so here I am having 2. So 1 plus 1 will be 2. 2 minus 1 by 2 minus 1 by 2. That means 2 minus 1, because minus half will be minus 1. So 2 minus 1 will be 1. So the final answer for this question will be equal to 1. So did anyone got the answer to be 1? Someone given 0 and Siddharth is given 2 and Sivaranjana has given 0. Can you guys check once with your calculation and let me know? If anyone even got the answer 1 also, you can let me know. Shyam, even you also got 0. Can you check? Is there any calculation mistake outside there? So this is our function, right? So for 1, if we differentiate, it will be x minus x square by 2, correct? And x square by 2 minus x. Limits here are 0 to 1 and here 1 to 2. So if we substitute 1, 1 minus 1 by 2. So 0, no need to substitute. If we substitute 2, so 2 square. So 4 by 2. So it will be 2 minus 2. So after substituting 2, the term will become 0. And then we are having minus. So this will be a single term, right? So minus of one term should be done here. So minus of, if we substitute 1, it will be minus 1 by 2 minus 1. So I am just multiplying the minus. So it will become minus half plus 1. So anyways, this substitution of 2 will become 0. And I will be remaining with my first and last, that is 1 minus 1 by 2 and 1 minus 1 by 2. That is nothing but 2 minus 1 by 2 minus 1 by 2, which is 2 minus 1. And 2 minus 1 is nothing but 1. So the integral value here will be equal to 1. So I hope you guys got this one. So anyone has any doubts? Because no one has given me the answer to be 1. Some has given to be 0. Some has given to be 2. So that you can just cross check the solution once. You can cross check the calculation which you have done. Okay, Siddharth, okay, 1. Fine. So anyone has any doubts in this particular concept? In this particular application of this property 3? If not, we can move ahead with our next property, guys. Okay. No, it's fine. Most of you given 2. Sorry, 1. Okay, fine. So let's move on to the next property here. So here comes the next property. So property 4. So if we are having integration of function f of x dx from the limit 0 to a. So it can be anything. Right. So then what I can do is, instead of leaving it to be f of x, I can actually write that to be, in place of x, I can write my sum of these two limits, that is a plus 0 minus x. So then that is nothing but a minus x. So in place of x, I can replace that with a minus x. So this is one of the property. So we mostly use this property when we have this trigonometric functions. Because in our trigonometric functions only we will be having our quadrant system. If we are having pi by 2 minus x, that can be written normal x according to the quadrant system and all. So that's why mostly we could see the application part of this typical property in our trigonometric functions. Right, so what is our property? So if we are having a integration of function f of x with limit 0 to a, so that can be, in place of x, we can replace that with sum of these two limits, that is a plus 0 minus of the x. That means directly a minus x, because one of the limit here is 0. So this integration of function f of x dx within the limit 0 to a can also be written as integration of function f of a minus x dx within the limits 0 and a. So this is the most important property when it comes to our trigonometric functions because it is most applicable in our trigonometric functions. So moving on to the next property here. So the same thing here. So initially what we have seen here, it is 0. But in this property 5, instead of 0, here we are having a limit value, that is a to b. So as I mentioned, so in place of x, what can be substitute? Sum of these two limits, that is a plus b minus of our x. So in the previous property also we have done the same thing, but in the previous property one of the limit is 0, that's why it directly become a minus x. So here both the limits are not 0, so that's why we will be having a plus x minus, a plus b minus x. So if we could have an integral f of x dx within the limits a to b, then that can be written as integration of function a plus b minus x dx within the limits a to b. So based upon the question, we can see and simplify it whatever it will be. Right, so the thing here is, it actually makes our trigonometric functions to simplify a bit easily when we apply these properties of 4 and 5 when we are solving and finding our definite integrals. Right. So let's solve a question here. So here comes our first question, which is related to trigonometric function as well as our properties 4 and 5. So now can you think of why we have done, what is the use of this? As I mentioned, mostly will be applicable. We'll be using that properties for our trigonometric function. So here comes the first question. So first question, as it's for your practice, I just given the RHS also so that you can just have an idea how to do it. So from the next questions, we can simply do it. So can you guys give it a try? So here it's actually our property 4 because one of the limit is 0 here. Quickly guys. If anyone has any doubts, any questions, you can ask me. So once we apply our property, then you will be having an idea how to proceed further. So how can we do it? So let's see what happens if we substitute in place of x, what we are going to substitute, that is pi by 2 minus x. Right. So let's just do that. So integration from 0 to pi by 2. So sine square, here I am going to substitute pi by 2 minus x. And in place of sine here, I am going to substitute pi by 2 minus x. Plus here I am going to substitute cos pi by 2 minus x dx. So then if I substitute pi by 2 minus x, in which quadrant the theta will be lying here? In first quadrant, as it's a multiple of 90, that is pi by 2, there will be a transformation according to our quadrant system which we have learnt. So here sine square pi by 2 minus x will be turning out to be cos square x according to our trigonometric quadrant system. And here sine of pi by 2x will be converted to cos x here. And this will be converted to sin x and dx. So now if you observe, this is our given question. This is our given integral. Our given integral, and after applying our property, the integral is having the same denominator. So there is no change in the denominator, whereas we are having here a change in the numerator part of it. Yes or no? So then, but if you even observe it here, So by looking at these two expressions, can you think of how to proceed it further? So by comparing these two expressions, our initial expression as well as the expression after applying our property, there is no change in the denominator, whereas the change in the numerator. But even that, in the numerator, one is sin square x and the other is cos square x. So if we identify what is the relation between what is the identity we have for this sin square and cos square x, we are having the identity that is sin square x plus cos square x will be 1. So now what I'll do, so I'll take this to be 1 and this to be 2, and I am gonna add these two expression. Right, okay, Siddharth has already proved it. Okay, good. So let's see. So let's just add these two, which means I'll be having sin square x plus cos square x in the numerator, and in the denominator I'll be having sin x plus cos x dx. So this is nothing but if I taken this to be I, and if I taken this will also be my I, then I add this will become I plus I, that is 2I. So now it is integration from limit 0 to pi by 2 of the function sin square x plus cos square x divided by sin x plus cos x. So now it will be 2I here, and then here integration from 0 to pi by 2, numerator will become 1, which is dx will be here, and then denominator sin x plus cos x. So now after applying my property, I end up having my I function will be equal to, so let me erase this. So my given function will be turned out to be 1 by 2 integration of 0 to pi by 2 dx by sin x plus cos x. So far if anyone has any doubts, you can let me know. If not, we can proceed ahead. So here we are having 1 by 2 from integration of limit 0 to pi by 2 and the function dx by sin x plus cos x. Right. So here this sin x and cos x can be converted into a sine function by multiplying and dividing with 1 by root 2. So as I am dividing here 1 by root 2 and 1 by root 2, I have to multiply in the numerator, which means here. Yes or no? So if I do it, what will be my expression now turning out to be? So this will be 1 by 2 integration from 0 to pi by 2 and dx. So again root 2 will be there because I have multiplied here. And this 1 by root 2 can be written as cos pi by 4. And here sin x will be there. Plus here 1 by root 2 can be written as sin pi by 4. And cos x is already there. Right. So now this entire expression, how can we, here as root 2 is constant, I can pull it out. So 2 root 2 here, and then integration from 0 to pi by 2. And now this whole thing can be converted into sine of pi by 4 plus x according to our trigonometric formula. Right. So once we have 1 by sine function can be converted into cosecant, because 1 by sine will be equal to cosecant x. So now my function will be turning out to be 1 by 2 root 2 integration from limits 0 to pi by 2, and then sine will be converted into cosecant x plus pi by 4 into dx. So now this is my final and simplified expression after applying my property here. So now I have to integrate this expression, and then I have to substitute my two limits here, which will give me the final answer here. So let's do that also. So integration 0 to pi by 2, and here we are having 2 root 2 here already. Yes or no? And then we are having cosecant function x plus pi by 4 into dx. So what is the integration of cosecant? So if you observe, the answer is in terms of log. So we have to use the formula of cosecant, which involves the logarithmic. That means 1 by 2 root 2 will be there, and the formula will be log of tan x. That means tan x plus log of tan x by 2. So that will be the formula. So here it will be x by 2 and pi by 4 into 2, it will be 4 by 8. And I'll be having my intervals here, that limits here 0 to pi by 2. So what is my formula of integration of cos x? That will be log of tan x by 2. So this will be my integration of the function cosecant x. So now once I have substituted here, I have simplified my integral. The next thing is, in place of x, I have to substitute this pi by 2. Right. So you can see it here, 1 by 2 root 2 log of tan x by 2 plus pi by 8. The limits will be 0 to pi by 2. So first thing we have to substitute is pi by 2. So then it will be 1 by 2 root 2 log of tan. If I substitute pi by 2 here, this will become pi by 4. So pi by 4 plus pi by 8 here. Right. And then I have to substitute 0. If I substitute 0 here, so this term will become 0 and I'll be having only pi by 8. That means log of tan of pi by 8. And in this will be the further whole. Right. So this will be the term once I substitute here my pi by 2 here. So can you guys simplify and prove it to the RHS quickly and let me know. So far only Siddharth has proved it. So I just simplified here so far. You can just simplify it further. So I can take log to be common and I can rewrite this term to be tan of. So pi by 4 plus pi by 8 will be 3 pi by 8. So tan 3 pi by 8 divided by here tan pi by 8. One more simplification step. And 1 by 2 root 2 as it is common. And tan 3 pi by 8, by using our pi by 2, we can convert that into cot pi by 8. According to our quadrant system. So 2 root 2 log of cot pi by 8 divided by tan pi by 8, because we can change our 3 pi by 8 by pi by 2 minus and we can written in this way. Right. So then we'll be having square here. So if I write 1 by tan can be written as cot. So this will become cot square pi by 8. And that square term can be taken to the head because it's a logarithm. Then it will be becoming, so let me erase this. So we are having 1 by 2 root 2 log of cot pi by 8, and in the denominator we are having tan pi by 8. So that can be written as here cot pi by 8, which will become the square of it. That means 1 by 2 root 2 log cot square pi by 8, and this square can be bring it on to the front because it's a logarithmic. So this will be 2 by 2 root 2 log cot pi by 8. And 2 and 2 will be getting cancelled and we'll be having 1 by root 2 log, and cot 8 value cot pi by 8 value will be equal to 1 plus root 2. So it's direct. So this is our final answer here after the integral, that is 1 by root 2 log of 1 plus root 2. Okay, even Arun has solved it. So the only thing here we should do is we have just applied our property 4 and then we have added our two expressions so that our numerator can be eliminated and we'll be remaining with only the denominator. And even in the denominator, we actually had the expression such a way that sin x plus cos x, which could be converted using our trigonometric format into a sin a plus b form. Right, so we have turned into be a single sign expression, and then we have once we have 1 by sign, that can be written as cosecant, and then the final expression we end up having in terms of cosecant. If we have in terms of cosecant, we have the direct formula for a cosecant, integration of cosecant in terms of logarithmic. So that we have applied and further simplified it by substituting our limits 0 and pi by 2. So this will be our final answer that we have to prove here, which is 1 by root 2 log of 1 plus root 2. So I hope you guys got this point. Even Siddharth and Arun has also proved it. Good guys. So let's move and do one more question here. So I hope this will be easy for you guys to solve it, because one thing I have already clearly explained how to apply our property and how to solve it. So now it's time for you guys to solve this question. So by looking at the limits itself, you might have an idea that how to start off this question. What is the value of this question, guys? Quickly. It's a very easy one. So let me know if you guys are facing any questions, any doubts. Okay, Siddharth has given the answer. So let's see how many of you can get the answer. Okay, Shivaranjani also given the answer. Okay, Arun also given. So 3 of you has already given the answer. So let's see what about others, guys. So the same way, the starting of the question will be the same thing. So I am taking this to be I. Right, so this is my I. So I equal to 0 to pi by 2 log of 4 plus 3 sin x by 4 plus 3 cos x. So this is my given question which I have taken to be I. So now I am going to apply my property here. That is, in place of x, I am going to substitute pi by 2 minus x. So then it will be 0 to pi by 2. So let this be equation 1, guys. And after applying our property, let's see what it turns out. So 3 sine of pi by 2 minus x. And here 4 plus 3 cos of pi by 2 minus x. And this whole will be the dx. And according to our trigonometric quadrant system, this sine of pi by 2 minus x will be converting into cos x, and then cos of pi by 2x will be converting into sin x. So now my expression will be turning out to be 0 to pi by 2. So log of 4 plus 3 cos x and 4 plus 3 sin x and the whole dx. Right. So now if you observe, so this, if you compare with, so let this be equation 2. So if we compare our both equation 1 and 2 here, equation 1 is having 4 plus 3 sin x in the numerator, whereas in our equation 2 we are having 4 plus 3 cos x in the numerator. So this can be rewritten as, so minus of log integration 0 to pi by 2. I am just changing the numerator and the denominator, that is 4 plus 3 sin x by 4 plus 3 cos x into dx. Right, so now I can add these two expressions. Right, so this is also I and my, so let this be equation 3. So my equation 3 also I and equation 1 also I. So now I am going to add 1 and 3. That means I plus I. So this is log the same expression minus of the same expression will become 0. That means 2a will be 0 whereas my I will be 0. So when I equal to 0, that means my question is nothing but I that we have assumed in the beginning. That means this expression will be equal to 0. So the integral value here, that is log of integration of log of 4 plus 3 sin x by 4 plus 3 cos x within the limit 0 to pi by 2 value will be equal to 0. So I hope most of you has given the answer, guys. So I think you guys got this point. So let's move on to the next one. So let's do one more question and then we'll just wind up our session with this question. So quickly solve this question. So if we start with it and you can simplify it, that will be fine. And the rest will be the same thing as you can see. So here if you observe, if we change into sine into cos also, there is no use right now. Right. So if we even change into sine into cos, if we add also, there will be no terms getting eliminated because there is no square here and we will not be getting the same denominator here. So now how will we be solving this? Now recall your indefinite integrals where we have discussed in our special trigonometric functions how we are going to solve when we have a single function of sin x or cos x. How we are going to rewrite this and simplify it. So now what we are doing here, we are getting into the methods which we have learned in our indefinite integrals. Right. So here using that, how can we write our sin x and how can we rewrite this complete expression? So you can try this later as homework. I'll just give you the hint how to start off this and how to simplify it. So this is according to our second type of special trigonometric functions which we have learned in our indefinite integrals. So if we are having sin x, this sin x can be written as 2 tan x by 2 divided by 1 plus tan square x by 2. Right. And if we write in place of sin x this entire expression, we actually converting the given integral in terms of tan and we even have in terms of secant. So now as our entire term is converted, entire integral expression has been converted in terms of tan and secant, and then we are going to substitute t in place of tan x by 2. Right, so now you might think we are having only the tan term here, but what will be the differentiation of our tan? So differentiation of the tan function will be the secant square function only, right? So you can substitute this entire function in place of sin x and you can simplify the integral, and then the entire integral will be converted into the expression in terms of tan as well as secant, and then you can substitute t in place of tan x by 2 and the further will be the same thing and you can simplify it easily, and after integrating it you can just substitute the limit values 0 and pi by 2 here, and that will be your final answer for this question. Right, because if we try and apply our any of the properties, even we applied, there is no use actually, because here there is no square, so that we can apply our identity of sin square x plus cos square x. And even if we apply our property, the denominator will also be not the same. So in any direction, if we check out, there is no use of applying the property right after the question in this particular format. So we have to convert that and substitute here and then we have to simplify it further. So maybe at the after simplification, if we might require, then we can do it. If not, we can just simplify the integral as usual. How we'll be simplifying a trigonometric integral using our methods, and then at final we'll be substituting our integral values, the limits for the integral, and we'll be getting the definite value. Right. So this is how we have to start this question. So I just given you the hint to start off this question. So please give it a try, guys. So take this question as homework. Please give it a try because it includes both our concepts of indefinite integral as well as the definite integral. So you have to make sure you have to try this question and let me know if you are having any questions and doubts in this particular question. So that's all for today. So we have started off with our properties of integrals. So we are having few more properties of integrals that we are going to cover in our next session of definite integrals. So if anyone has any questions, any doubts, you can let me know, and you just try this question for homework and let me know if you have any doubts in our next session in this regard of the question. So that's all for today. So we'll just continue the rest in our next session, guys. So that's all.